Okay, so this video, 5.6, our first day on it, involves related rates. We can look at the notes here and see that what is a related rates question? Well, in the real world, the rate at which one variable changes can directly affect the rate at which something else changes. For example, if the radius of a pumpkin gets larger, and again, we're thinking over time, perhaps this pumpkin is growing and the rate of growth might be very small. But regardless, the radius of the pumpkin gets larger. We would expect that the volume of the pumpkin will also get larger. Another example, if a ladder slides down a wall and the base of the ladder is getting farther away from the wall. Well, I've drawn in a little bit of a picture off to the side here. You can see here's this ladder. The base is sliding farther away from the wall. We can see that eventually this ladder, which of course, whether it's a 10-foot ladder or whatever height that ladder is, it's going to always be that same distance of a ladder, but that base has slid out. The height of the ladder, the height that the ladder reaches, will decrease. In blue, you can see I drew the ladder as the base slid out. You can see that this top of the ladder here, the height of the ladder on the wall, is going down. Uh, I hope it's pretty obvious that really what's happening is we're looking at a rate of change with respect to time. And that's so incredibly important. I think it's very important for us to realize that when we take derivatives, very often we use the chain rule. So, just for some review, let's just say that I wanted to take a derivative of, let's say, some function of time, and if we had a square here, and if I said take a derivative with respect to time, well, we'd say bring down the 2, then we'd have f of t, but then we'd say multiply by the derivative of that inside, f prime of t. And another way we could write f prime of t would be df dt. You've seen that written a number of times also. Why do I bring this up? The chain rule is going to be at play here all throughout today's lesson. And in fact, when you take the derivative of that inside part of the function, you're going to see quite a few rates of change with respect to time. In fact, the lesson that we're looking at right now very frequently is thrown in right after students learn the chain rule. And I think it's pretty obvious why that could be the case. But let's say that you want to assume that the radius of a sphere is a differentiable function of time. What I really want you to think of is you think of a radius of a sphere from geometry. The volume of a sphere is 4/3 pi r cubed. Now, when we're looking at this, both the radius and the volume are really functions of time. Another way we could have written this would be v of t equals 4/3 pi. Here we'd have r of t raised to the third power. Why would I even want to write it that way? Well, to remind you that we're going to have a chain rule here. But let's go ahead and take a derivative on the left with respect to time. Very simply, we'd get dv dt. On this right side, well, look, just slowly dropping this down, we can bring down to 3. We'd get r squared, but then we take the derivative of the inside. We get our dr dt. The 3 and this 3 down below cancel out. Final answer would be dv dt would equal 4 pi r squared dr dt. So we've got these rates of change coming into play. Let's say that we also have a cone. And when you have a cone for part B, and if you wanted to take a look at the volume of that cone from geometry, we're going to have a lot of review of geometry today. The volume of a cone is 1/3 pi radius squared, or 1/3 times the area of the base, times the height. But it's important to realize in this problem that the volume and the radius and the height are all functions of time. And v itself is a function of time. So the derivative on the left would just be dv dt. On the right, though, we have two functions of time that are going to get multiplied together. We will need the product rule. Here's r squared. Take your derivative of the second function, you'd get dh dt, taking a derivative with respect to time. So you have your uv prime, so to speak, first function times the derivative of the second, plus, now take the derivative of your first function, be careful, 2r dr dt. You need that derivative of the inside, that's coming from the chain rule, times the second function. So that's like your uv prime plus u prime v. Of course, we could distribute that 1/3 pi in there. We could just as well leave this as our final answer. So either way is fine. Just to tell you the truth, though, so far we haven't dealt with the challenge of actually writing out an equation and building a related rates problem up from ground zero. So very often you'll just read some basic information and you'll have to make an equation. We're going there right now. Most of the problems you're going to be doing will require that we do a sequence of steps. The very first thing that you'd like to do is to draw a detailed and labeled picture. Don't have any numbers in that picture unless they are fixed or constants. For example, if we were to go back to this ladder problem that we had, the length of the ladder, perhaps it's a 10-foot ladder, is always going to be the same, regardless of where it is sliding. The distance from the base of the ladder to the wall could change. The height, the distance from the tip of the ladder to the ground will be changing, but the length of the ladder itself is fixed. So use variables very frequently for items that are changing, that vary. That's why we call them variables. But use fixed numbers, constants, when you have a definite, constant, fixed length. Number two, listing the variables and their rates. Very often in the information as you're told about the problem, you might very well have a given rate. And that rate might even be just for one particular instant in time. But fill in what values you know. As you're looking around, hopefully then you can write an equation. As you're looking at the picture, something will jump out where you can relate the variables and the constant perhaps together. Think geometry and trig formulas, and we'll get into that in just a moment. Then take a derivative of the equation, with respect to time, of course. Solve for whatever piece of information you are looking for as a final step. Take a look at some very common formulas. The Pythagorean theorem will show up in many of these problems. It's used for finding missing sides. I've written the Pythagorean theorem backwards with the hypotenuse, the side across from the right angle, isolated. C squared would equal a squared plus b squared. Volume of a cone, we already dealt with that just a moment ago, but that shows up in quite a few problems. The volume of a sphere, we dealt with that as well. V equals 4/3 pi r cubed. Surface area of a sphere. Well, the surface area of a sphere, of course, we would have a 4 pi r squared. And really, sometimes, very frequently, we're going to need SOHCAHTOA. SOHCAHTOA shows up so much, and we definitely have to be on our toes to see what we have. But let's see one of these problems in action, and we need to carefully read through this to find out if there is a given fixed length or a quantity that we can put in, as well as variables, lengths or values that are changing. This problem says a hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. So we've got a balloon, and you can even call this point B if you'd like. It's moving upwards. It's rising up. Its height or its distance from the ground is not fixed. It's going upwards. This rangefinder, we could say over here, R though, is in fact 500 feet from the point of liftoff. I hope it's obvious that the 500 feet is in fact fixed. This rangefinder that is going to be measuring an angle of elevation, and we're going to see that in a moment, will always be 500 feet from the point of liftoff. But it says at the moment of the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.4 radians per minute. The phrase at the moment is a friendly reminder to let you know that this angle is not always going to be pi over 4 radians, or equivalently 45 degrees. Rather, this angle of elevation will just, for one brief instant, be pi over 4. So we could even begin to draw this in and say, well, my goodness, look, there is an angle. I'm going to just write it as theta, though, because it's not guaranteed to be fixed at pi over 4. It's changing. And in fact, at that brief moment, the angle is increasing at a rate of 0.4 radians per minute. This is telling you d theta dt would be 0.14 radians per minute. How fast is the balloon rising? Well, the balloon is rising, you're really asking how its height is changing. You're asked to find dh dt, and we don't even know what h is. But suffice it to say, once you've labeled your picture, you've written in what is constant, what it is that we're given some information about, a momentary information about an angle, so we need a general angle, theta. We know that we're asked to find the rate of change in the height, how fast the balloon is rising. That means that h is a part of this problem as well. The Pythagorean theorem might seem to be very helpful here, but it's not, unfortunately. The Pythagorean theorem relates three sides of the triangle. Instead, because we have an angle, I hope it's clear that we're going to need SOHCAHTOA. SOHCAHTOA is going to allow us to work this through, because here's our angle. This would be an opposite side. Down below is the adjacent side. I hope it's clear. The equation that we're looking for is tangent. Tangent of theta is equal to the opposite side h divided by the adjacent side of 500. And right now, theta and h are functions of time. Let's take derivatives. The derivative of tangent is secant squared of theta, but then with the chain rule, we'd have d theta dt. The derivative of h would just be a 1. So I'd just have 1 over 500. Or you could just say it's dh dt, taking a derivative of the inside part. Just like we took derivatives implicitly, like the derivative of y, you could say is dy dx. You could think of the derivative as h as dh dt just as well. But now we can pull in some information. We can say just for the briefest moment, theta will equal pi over 4. D theta dt will be 0.14. And here we have 1 over 500, and we have our dh dt. All we have to do is solve. Now, I hope you know that the cosine of pi over 4 is radical 2 over 2. And another way to write radical 2 over 2 is 1 over rad 2. So the secant of pi over 4, the reciprocal, is simply rad 2. So if I'm squaring the secant of pi over 4, I'll have a 2 itself. So this just becomes a 2 times 0.14. Then over here we